All right, so this is your problem, page 540. So a can of dog food contains 500 cubic centimetres of food. The manufacturer wants to receive the maximum profits by making sure that the surface area of the can has optimal dimensions. All right? Let the radius of the can be R and the height be H. Find the dimensions of the can that will have the minimum surface area. Now, you can see that's an exam style question. There's no real clue as to what you're supposed to do, right? It's not like do this to solve this problem. You have to recognize this as this topic. And there is one clue. What's the one clue? Almost that bit, just before it. Well, this word, optimal, mate, yeah. All right, optimal, maximum, okay, those kind of words. As soon as you see that, that puts it in this topic, right? We're probably going to be doing, you know, to get full marks, we're going to be doing some differential calculus, you know, working out gradients, that kind of thing. All right. Do you remember what I said would become the most important part of the gradient functions and things? So I said there's one value of gradient that you're going to get really used to using and looking for and calculating where it is, and that particular point on the curve had a certain name. Nope. Nope. So the gradient, that's what gradient is, but there's a particular value of your rate of change that goes with this word maximum or minimum. Turning point, yeah. So that's a turning point. And what do I know about the gradient at a turning point? 0. So remember I said those are going to become super important for you, all right? And with a lot of these problems that are applied problems like this, that's what you're looking for. The problem comes with setting up the equations in the first place, all right? And you will also refer to your formula booklets, because this is about volumes and surface areas of three-dimensional objects, and you have formulas for those three-dimensional objects in your formula booklet. All right. So again, with these kind of problems, take every bit of information you've been given. Let's not try and remember formulas. Let's get your formula booklet out, look at it. So I don't know, you probably haven't got them at this stage, but let's have a look. First thing is a diagram. Let's draw a diagram. Let's set this scene. So what will it look like? A can of dog food contained, well, what does a can look like? It's a cylinder. So we would do a little diagram of a cylinder. Okay. However good you are at art. It says contains 500 cubic centimeters. That means the volume of this cylinder. Why didn't that come out? The volume is 500 cubic centimeters. Okay. I'm taking all this information out because quite often there's marks for, oh, they've identified that the volume is. Yeah. We've got lots of other information. The manufacturers want to maximum, blah, 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 optimum dimensions. Then we've got let the radius be R and the height be H. So on the diagram, that means from the center out here will be R, and the height of the can will be H. So we'll label that. So now we've taken all the information we can. The rest of it is all about doing something. But there's one thing, like I've already said to you, you can write down that's not in the question but is available to you, and that is the formulas for a can. And we are given two pieces of information. One is volume. What's the other piece of information? Surface area, right? We are told to look at surface area. So I've got two things I want to write down, okay? The two things I want to write down are, well, what is the formula for volume of a can? So I've got that. And I then want to know what is the formula for the surface area. So either you remember them. There is pi r squared is part of it, yeah, because that's part of that's the circle. Pi r squared is the area of the circle. So we do have pi r squared, but you have one on the top, one on the bottom. So you have two of them, 2 pi r squareds, all right? Well, you're mixing two. So the volume, I think what you're saying is pi r squared on its own is the area of the base. So for any shape, like a simple shape like this, you have the area of the bottom multiplied by its height. So if it was a cuboid shape, you work out the area of the rectangle and then you multiply it by the top, yeah, the height. So this is a circle, so that's the circle on the top or the bottom, doesn't matter. And then we multiply by the height. So we have pi r squared, h is the volume, right? The surface area is the shapes of each part. So the surface area of a cylinder, well, we basically have pi r squared, which is a circle, but we have two of them because top and bottom, yeah, bottom and top. What do we also have of a cylinder? But what's the other shape? What's the surface? So we've got the circle on top, circle on the bottom. We actually have the curved surface. If you remember back in the day, what shape is that? If you cut open a can, oh, you've probably done it with other cylinders and things. I know I've done it in previous years. Take the circles off. If you then slice down the side of the cylinder and open it out, what shape do you have? A rectangle. So we actually have a rectangle like that that just wraps around. So what are the dimensions of? So this is 2 lots of pi r squared, which is that, plus, but what are the dimensions of? Pardon? It's length and height. So I've got height, but the length is what? So how long does it need to be to wrap around the circle? It needs to be the same length as the circumference of the circle. And anyone remember what the circumference of the circle is? So you've got the circle that sits, it wraps around. So the formula for a circumference of a circle is, it's either pi d or 2 pi r, because 2 r's is a d. So I'm actually going to call it 2 pi r. Why have I chosen pi r instead of pi d? Because you've got radius. Yeah, exactly that. So then that is 2 pi r multiplied by h. So we have 2 pi r h. Right? But again, a lot of working that out. You don't need to. It's in your formula booklet. Go to it. All right. So we've got two formulas. All right. What are we going to do? We need, it says, let the radius of the can be r, find the dimensions of the can that will have the minimum surface area. So basically, if I change r, right, the radius of the can, that will change the height automatically. Why? So if I make my can fatter, the can will have to get shorter. Why is that? There's one thing that's been set in stone in this question, which is the volume must be 500. And the reason for that is they know they want to give that amount of food, right? They just want to maximize their profits on the can. So they want to know what R and... So if I work out R, H is set in stone anyway, isn't it? We can work that out. So what we can do is set it up in terms of R, which is quite good, right? So, any ideas what we could do at this stage? We've got lots of information, but it is still just information at this stage. Well, we've got two equations, one for volume, one for surface area. But when we've done our differential calculus, we've only ever used one thing, yeah? So what we need to do is combine the two and have one. So the one thing I haven't done yet is I haven't stuck those things together. So would you be happy enough if I then wrote, instead of volume equals, would you be okay if I wrote pi r squared h equals 500? Because that's the formula for volume. This is the volume. Okay. All right. Any ideas what the next step would be? These are tricky, by the way. I mean, difficult questions. Lots to it. This would be a big question. It'd be like 17, 20 mark. Lots to it. There's lots of steps. This bit, the first bit, is hard, right? Setting up these equations. So the first thing we need to do, remember I said I need to combine these two because I've got R and I've got H, but I only want R. I don't need two unknowns. So if you remember your time from simultaneous equations, yeah? Do you remember what methods you have to solve simultaneous equations? So you have the elimination method where you do one, subtract the other, but you also have what's called a substitution method where you rearrange one of them and then put it into the other. And that's the method we're going to do. So I'm going to rearrange this one, okay? And I'm going to make it H equals. And you'll see why. So do you know what that would be? Yeah, what would this side say? I'm rearranging this one here, okay, rearranging this to make it H equals. And the reason why I'm doing this one is because this one has got R, H, and surface area with no information. So I can't rearrange this one. This one I've got more information, so I'm going to rearrange this one. We're going to rearrange the one that they give you a number for, right? It's always the way. So what would I do? Well, this is pi times r squared times h. So really, if I want to get rid of the r squared and pi, I just do what? Divide. So divide by pi and r squared. So I've got h equals. So any ideas what your next step might be? Well, I've used this one, so that's kind of out of play now. I've used it here. Now I'm going to focus on this one. And the thing with this one, I want to be left with R. So I've got a H here. Yeah. Let me a bit better. So I've got a pi r H in that, and I've got a H equals over here. So what I'm actually going to do is take this and replace the h with it. Because h equals that, and that's a h, I can replace any h with all of this. That makes sense? So I rewrite it then. So this surface area now becomes surface area equals 2 pi r squared plus 2 pi r times, I'm going to put it in brackets, all of this goes in 500 divided by pi r squared. It replaces the h completely, yeah? Use brackets. Now we've got some simplifying that we can do, which will be quite nice, all right? Because it looks horrible at the moment, but if I do this, if I expand this bracket, so multiply out, what do I end up with? Any ideas? So surface area is now 2 pi r squared plus okay, 1000 pi r still divided by pi r squared. It is, yeah, because when you multiply a fraction, you multiply the numerator. You divide a fraction, you multiply the denominator. But there is something we can do now with this fraction, which is good. Cancel out. So the pi's cancel, and this r cancels with one of those, yeah? So we're now left with surface area is 2 pi r squared plus 1000 all divided by r. So this really, we've not even started our optimization yet. We're just setting up a formula for surface area, okay? And this is why I said your algebra, your ability to work with algebra formulas, manipulate, has to be good to get to the stage, right? The assumption is you can do all of that. All right, so what we're going to do then is we need to find, all right, the best value of r. Okay. All right, so what do we want surface area to be? Do we want it to be, when it says in the question, let's go back to the question, let's just check. It says, find the dimensions of the can will give the minimum surface area. So that also makes me realize the surface area was the correct way to go, yeah? Find the minimum surface area. So I want to know where this is a minimum. There's now a super easy way to do that. What can we do? This is in a differential calculus topic, but it's not always necessary for a question like this to use differential calculus. But if it says find the minimum, what would you do? Come on, computer, the computer's really slow. What am I going to do with my calculator? This, yeah, exactly. Y equals, what am I going to type in? 2 pi up here, second pi. What do I do for r squared? X. Just x or x squared? Yeah. Plus, so I'm going to put in my fraction thing, just so there's no issues at all. 1000 divided by x. enter. All right, I'm going to graph it. It's broken. Yeah, yours is broken too then. Or is it? Or is there something we can do? Yep. We can actually, to start with, I don't know if you've checked it, if we go to window, I think, there's something, I want to go to, oh, hang on, let's zoom. Sorry, I'm messing around. I go to zoom. Right, if you click on the zoom button, all right, there is an option, if you go down, to zoom fit. If you press enter on that, okay, get zoom fit. Yeah, it fits it. It might not be perfect for what we want, but it gives us a good starting point, yeah? Especially in an exam, if you're messing around, zoom fit works nice. All right, but this is where the understanding comes in. What's this graph all about? What's the equation about? So this graph tells me the surface area of the cam. Yeah? X is R being the radius. So looking at this graph screen, is there anywhere that's just a bit irrelevant? Why? Exactly that. So this graph, the zoom fit, nice, but it's like, oh, what do I do? Actually, when we go to window now, okay, go to window, I don't need a negative X. That doesn't make any sense. But that is 0, okay? I definitely don't need a negative surface area. Let's put that at 0, okay? Now we graph it. Now we've got the relevant material, all right? And we are now looking for what? The, nope. Yeah, that would be a maximum. Maximum is a turning point. We don't have a maximum as a turning point. What do we have as a turning point? Minimum. That's what we're looking for, right? The minimum surface area. Can you see? It's a slightly tricky one on this question, but can you see it comes, look, when R is really small, we've got a massive surface area. Imagine that. Yeah, imagine a can that's like the thickness of a pencil, right? All of that material is one long straw, basically. So straws have a high surface area for the volume, right? As you make R a bit bigger, the thing shrinks in terms of height, but the volume, the surface area gets lower, all right? But it becomes more manageable. And then when R gets even bigger, the surface area will get bigger again, but only slightly. It doesn't rise up in the same way it came down. So there is a slight rise. So around here is what we would call our local minimum value. And we need to find that, and you know how to do that, which is? So yeah, second trace for calc, find the minimum, press enter, left bound. So I'm going to take my cursor to somewhere where it's going on the up. Doesn't really matter where. Let's make sure I can see it. Press enter. Right bound, I'm now going to go somewhere else, the other side, so I can see it. I don't know whether... There you go. I know I'm to the right of it. Enter. And then when it says guess, I'm going to go somewhere roughly where... It doesn't really matter. It's only going to look between those two values. Now, it's not very clear because I've got overlap. The best way to sort that out would be to add a negative y values to lift the whole graph up a bit. That might make it clearer, but it's there. If I press enter now, look, it's going to tell me my minimum is about there. So that's got when x is 4.3. Yeah? Have you got 4.301? So the minimum is when r is 4.301 centimeters. Okay. That's when the surface area is a minimum. Let's just go back to the question. Have we answered the question? The question is, find the dimensions of the can that will have the minimum. So, yeah, well, I found R, but from my diagram, I can visually see I still need H. So how can we figure out H? Which one? Good. There's circles in these kind of problems. So where did we start? We started with volume, right? We go back to volume. So I now know, because of the number, that 500 equals, what was it, pi times 4.301 squared multiplied by h. Okay. And what do I do now? Well, actually, I had it already rearranged. I could have just checked. It's actually 500 divided by pi times 4.301 squared is equal to h. So h is equal to, you just got to chuck that into your calculator and tell me. So if I were to do it, I'm just going to clear that. So solve that. So again, I'm going to use my fraction button. 500 divided by, chuck it all in as it is written, pi times 4.301 squared. Enter 8.604. Okay, so I now have R is that, H is 8.60. That's rounded to 4 significant figures, but I'll probably have to round them to different values, 3 significant figures, but both should be in centimeters, and that's the dimensions of my can. All right. What have we not used? Not to solve the questions done, finished, but in terms of our mathematical ability and knowledge, what did we skip by having a calculator? Well, might not be obvious to you because this first one we've done, but when we want to optimize, we know it's a differential calculus thing, yeah? And on our calculator, we saw that we want to find a minimum point, yeah? What do I know about the minimum point? That's when the gradient is 0, right? So at this stage here, basically, I could graph it just to show we've got this graph exaggerating it. I am looking for this point here, all right? That value when R is, that's when I know that the gradient equals 0, yeah? How can I find that? Well, what we do is we take this point here, which we just chucked into our calculator. I'm going to call it surface area is equal to, right, 2 pi r squared plus, and I'm going to change it, you tell me why, to r to the minus 1. Remember doing that? The reason is because we are now going to do ds dr. So can you tell me what that would be? 4 pi r plus minus 1000 r to the minus 2, yeah? I'm doing that? Okay. Which I could then rewrite, if we want, as 1,000 over r squared. Yeah? Happy with that? So what am I then looking for in that situation? I'm looking for when it, so I now need to solve dSA over dr equals 0. So that's when 4 pi r minus 1,000 over r squared equals 0. All right? How do we do that? Most of the time when it's functions and I say, how do we do that? Your answer is probably going to be, use your calculator, yeah? So if we were doing the other course, you have to rearrange, solve a quadratic. I'm not going to worry about that because we've always got our calculator. So get our calculator out, but what do we do instead? Well, I'm going to switch that one off. I'm not going to delete it. This time I'm going to put this formula in. So I'm going to put 4 pi x minus, put my fraction in. Okay, it's 1,000 over x squared. Yeah. So let's graph that one. Oh, that's broken again. So let's zoom and zoom it. Enter. Okay. I want to know where it equals 0. So this is no good actually, even the zoom fit. So I'm actually gonna go, let's try minus 10 this time, although it's not relevant supposedly. All right, and then let's do, we've got minus 88,000. Let's just do minus 50 to 50. So sometimes that zoom fit doesn't work. I'm guessing completely. Click graph. All right. So it does cross. So the equals 0 bit is where it crosses the axis, isn't it? What value are we looking for? What do we think that x value is going to be? .3. So we just check, how do you find it? Second, calc, 0. Done it lots of times. Yeah, left bound, let's go. There you go, there's my cursor, enter. Right bound, let's go up to that right bound of it, enter. Guess, just move a little bit closer, enter. 4.301 again. Sorted. Yeah. All right. So we get the same, and then the rest of it is exactly the same. But do you think this bit we've just done is a little bit unnecessary to solve that problem? Why would it maybe necessary to be able to do that? Or just in an exam situation, they might want to check certain things. So that you're able to do it. So in the book, look, their solution, look, is what we just did. All right. So using your solver, what they've done is they've actually created this and done a solver method, but we've kind of not done much. So that graph method is fine. But we've got this situation, all right? Basically, all the formula and stuff is the same. Right? The hardest bit, like I said, is forming and solving the equations in the first place. That's the tough bit. All right? Okay.